Hi everyone, my name's Papacharissiou and I'm a developer advocate for Chainlink Labs, and today we're going to be talking about building secure smart contracts. So first things first, I just want you guys to imagine a scenario. Imagine as if you were the head of cybersecurity at a really big bank like HSBC or Bank of America or something, and you were the one that were in charge of preventing systems from being hacked and exploited. But on top of this, I also want you to imagine that all of the code for all of your systems is public, where anyone can see it, anyone can kind of see what's going on in there. On top of this, I also want you to imagine that all of the transactions going in and out of those systems is also public. Does it make you a little bit nervous as your job? And on top of this, I also want you to imagine that in the event that an exploit or vulnerability is found, that the transactions are irreversible, that you can't go to a credit card company or some other institution and have them reversed. So does this kind of make you feel a bit uneasy as your job as head of cybersecurity? Well, this is the exact scenario that smart contract developers face every day when building their smart contracts. Open code, immutability, open transactions are all great things that kind of have given a rise to this new industry. However, they also create a bigger attack vector for attackers and exploiters with smart contracts. So we need to be very careful when we build smart contracts and have a really security focused kind of overlook when we kind of try to create them. So in terms of security, it can generally be split into two different categories. There's issues with the underlying protocol and infrastructure, or there's issues or vulnerabilities in the smart contracts themselves. Now, we 100% need to be focused and look at the first category. However, the EVM and the protocols have started to mature over time and issues have been fixed. So for the purposes of this presentation, we're going to focus on this second category, bugs or vulnerabilities in the smart contracts themselves. So programming smart contracts requires a different kind of programming mindset, and they can be thought of as more like hardware rather than software, right? So with software, if there's an issue, you can just release a patch, send it out, everyone can install the patch, and then everything's fixed, right? Smart contracts are immutable programs that can't usually be changed once they're modified unless you pre-program it into the contract, which we'll get into later. So it can be thought of as more like hardware, where with hardware, you kind of, there's kind of like a recall and you kind of have to send it back and get a new one, basically. So in terms of smart contracts and vulnerabilities, we're going to go through the top 8 smart contract vulnerabilities that you as a smart contract developer should know. And we're going to see how they happen and what kind of things you can do to kind of prevent them. And we're going to go from descending order from number 8 to number 1, right? Now, some of you may know all of these. They're all public. None of them are kind of brand new. However, I feel it's good to be reminded of these from time to time. So vulnerability number 1 is timestamp dependence. Now, this is something specific to miners, and this is where miners can have a small window of a few seconds where they can manipulate the timestamp in a transaction or in a block, basically, to basically exploit a smart contract to their benefit. So I'll give you a good example of this one. So in the code sample here, you can see down near the bottom, there's a if now modulus 15 equals 0. So you basically get a 1 in 15 chance to win a lottery or something and kind of take the ether from the contract. Now, when a miner basically sees this, they can put the timestamp in a way where that will equate to true, and they can then take the ether. So you kind of need to be aware of that. So in terms of potential solutions for this, don't use block timestamps for any logic relating to the movement of funds. And if you do need time-sensitive logic, you can basically take an average block time of 10 or 15 seconds and then say, all right, I need something to execute in a week or something from now, and you can kind of forecast what the block number will actually be at that point in time, and you can kind of do that instead. So the next, number 7, smart contract vulnerability to watch out for is unexpected ether. Now, this is a really interesting one that revolves around the use of this.balance. And the way it works is you can't ever be sure that the ether in your smart contract has come in a normal manner, right? So usually you have fallback functions or payable functions in your smart contract to accept ether. However, people can forcibly send ether to your contract, and this can kind of cause some unintended results if you have logic around how much ether you expect there to be, right? So they can use a self-destruct function in their own contract, which will send ether to your contract, and there's nothing you can do about it. Even if you have a fallback function to kind of reject it, your fallback function will not get executed, right? So you can't protect against that. And in addition to that, smart contract addresses are deterministic for a wallet address. So people can know what smart contract addresses you're going to generate in advance, and they can send ether to that address before you've even generated a contract there. And when you do generate a contract there, all of a sudden it's got ether in there. So we'll go through a brief example here. As you can see, there's a payable function, a fallback function at the bottom that kind of reverts. So you think, yep, no one can send ether to this contract. However, if someone does a self-destruct on another contract passing this contract address as a destination, ether will get sent to this contract, and then that only non-zero balance function will be able to get executed by a malicious actor. Next one. So in terms of solutions for unexpected ether, don't rely on the use of this.balance for logic operations. And if you need to kind of track ether deposits and withdrawals and things, do it with your own custom logic in the smart contract, where you kind of can mitigate the effect of people forcibly sending ether to your contract. So the number 6 vulnerability to watch out for is transaction origin. Now, this is a command that can kind of traverse back in the stack and find out who the original address was that initiated a transaction. And basically, it leaves a contract vulnerable to phishing attacks if you use it for in specific ways, right? And the best way to show you this is with a little code sample here. So in this scenario here, there's a withdraw all function, and it validates that the Tx.Origin is the address that initially created the contract. It validates that, and then it transfers the ETH, right? And you think, yep, that seems pretty normal to me. However, what if that contract is owned by some big protocol, well-known company, and someone sends some ETH to it and then says to them, hey, I accidentally sent you $100 in ETH. Can you please send it back? It was an accident. Here's a signature that proves it was me. And this company says, all right, yep, that's fine. We'll send it back. And they send it back to this phishable contract here. And let me just go to the next slide. Whoops. And what this contract will do is it will then this fallback function will kind of get called down near the bottom here, which will then go back into that initial contract and execute the withdraw all function again. And all of a sudden, the Tx.Origin is going to be this contract here, and then the funds are kind of going to get stolen. So that's kind of how that gets exploited. So in terms of potential solutions for this, don't use Tx.Origin for authorization. And if you do want to kind of deny external contracts from calling a current contract, you can kind of use the syntax that's specified over there. So the next smart contract vulnerability to watch out for, number 5 out of 8, is delegateCall. Now, this is a really tricky one where basically a contract can dynamically load code from a different address at runtime as if it was in your contract, and it enables the use of what we call libraries in Solidity, right? So they're great. However, when you combine the context-preserving libraries with the context of another contract, you can kind of get this weird, unexpected behavior that can kind of lead to exploits happening. So in this example code here, we've got a delegate library contract and a delegation contract, and an attacker can call the delegate.pwn function in the context of the second delegation contract. And this means that pwn will basically modify the state of delegation and not delegate. And the result is that the attacker can take unauthorized ownership of this second contract here. So this kind of exploit was actually what was used in the Parity Wallet Exploit from a few years ago, where a malicious actor was able to attack a kind of a library contract, and they were able to basically exploit the Parity Wallet and basically take control and steal a whole bunch of users' funds. So in terms of solutions for this one, use the library keyword whenever you're creating these library type smart contracts, and ensure that the library, it will ensure that the libraries are stateless and non-self-destructible. So number 4 vulnerability to watch out for is the overflow underflow attack. This is a really simple one where basically you've got integers and data types that can only have a certain range, and if you go to the edge of that range and then add or subtract, etc., it's going to circle back around and you're kind of going to get like incorrect balances and incorrect numbers. So here's an example of 2 transfer functions. The first one is just validating that the sender has enough value, whereas the second one is validating that the sender has enough value and that when you add the amount onto the receiver amount, that it's more than the initial amount, right? So we're kind of checking for that overflow scenario there. So there were a bunch of exploits that happened a few years ago around this. Haven't been as many lately, however, it doesn't mean that we shouldn't remain vigilant around them. So in terms of solutions, you can use things like SafeMath that will kind of automatically check for these scenarios from occurring and let you know. Or if you're using Solidity V8, 0.8, it actually has integrated SafeMath into it, which is awesome. Number 3 attack you need to watch out for are DOS attacks. Now there's different flavors of these, however, they're all kind of similar in that they basically leave a smart contract inoperable for a certain amount of time, or they kind of trap ether into them in some way. So here's an example of a looping attack where you have an array that's kind of looped over to kind of send investors some tokens or something. And the way this can be exploited is if an attacker creates the array of investors so large, such as when the distribute function is executed, the gas that's needed to kind of iterate through that is going to be more than what you can actually have in a block on the blockchain, right? So you can never run that function. So an own operation DOS attack is essentially when a specific person or address needs to progress the state of a contract, right? It's specific to their account, and they can't do it for whatever reason. So, you know, they lost their keys or they were hacked or something. So it's not always a malicious actor, but you can kind of DOS attack yourself in a way if you lose your keys and then you can't progress your contract to kind of the next state. And finally, we have external call DOS attacks, where basically attackers can make external calls and contracts never return, halting contract execution, right? So if you're relying on an external call, you can't always assume that everything's going to act normally there and you're going to be able to proceed. So in terms of solutions for these DOS attacks, don't loop through data structures that can be artificially manipulated. You can have a withdraw function instead that each individual user needs to call. Use multi-sig contracts where possible instead of relying on a single owner to progress contract state. And for external calls, account for their possible failure, or you can use a time lock to progress the state of a contract where you can say, if the state hasn't changed after X amount of blocks, let anyone progress the state. The number 2 smart contract vulnerability to watch out for is front running, right? So this actually is a very hot topic at the moment and contributes to a larger overall discussion and issue known as minor extractable value, or MEV. And the way this works is basically transactions are visible in the mempool for a short amount of time before they're put into a block, and malicious actors can take a look at these transactions and then create transactions of their own to benefit themselves and put in a high gas price so that miners will choose their transactions first to their advantage. So this is popular with DeFi protocols and decentralized exchanges at the moment. And we see this happening every day. It's not just some small thing. It's becoming a larger and larger thing that we kind of need to watch out for. So in terms of current solutions, the best thing you can do is reduce the importance of ordering in your protocol if possible. Or you can modify the upper bound on gas price so that malicious actors can't kind of do this front running. Or you can use a commit reveal scheme where basically it splits it into 2 transactions. The first one is kind of hidden and the second one kind of reveals the information. In terms of upcoming solutions, Chainlink is working on fair sequencing services, which basically offloads the ordering of transactions to a decentralized Oracle network where you kind of separate the ability to produce blocks from the ability to order transactions. And if you're interested in this, there was a great talk yesterday by Chainlink Labs Chief Scientist, Dr. Ari Jules. The number 1 smart contract vulnerability you need to watch out for is the re-entrancy attack. Now, this occurs when a contract sends ether to another unknown contract, and that unknown contract usually has a fallback function that then goes back into the initial contract and does something malicious. So as we can see here, we have a simple withdraw balance function. However, the balance isn't actually modified until the very last command. And what a malicious actor can do is they can have a fallback function that when the ether gets sent there, it will then go back and call the withdraw function again, which will then basically keep taking ether out of the contract. So obviously not ideal. So in terms of solutions to this, use a transfer function when sending ether to a contract. It's only got a certain amount of gas that it uses, so the re-entrancy attack isn't possible. Or you can ensure all logic and state changes have occurred before doing these external calls. Or you can introduce a Boolean variable to kind of say what can and can't be done into the logic of your smart contract. So here's a simple solution where we've just modified the balance first, and then we're kind of doing the call after, and that will prevent re-entrancy. And so the DAO hack, actually, re-entrancy paid a large part of the DAO hack from a few years ago that created the Ethereum hard fork of Ethereum and Ethereum Classic. And it goes on to serve as a reminder that just the order of a few lines of code can have such a huge impact. Now, there are other vulnerabilities and exploits. Unfortunately, I don't have time to go through them, but I highly recommend looking into those as well. So now let's go through some considerations and best practices. So first things first, make sure you test your smart contracts. Make sure you have thorough tests, units, and integration tests. There are some great testing tools that you can use these days to kind of help you with the quality of your smart contracts as well. And if you find an issue with your smart contract, what some people do is they just basically fix it, create a new version, and say, hey everyone, that was the old one, here's the new one. That's fine, you can 100% do that. However, it does require a bit of social coordination. Some people create what are called upgradeable smart contracts, where they basically implement a proxy design pattern where the users interact with a proxy contract that delegates calls to an underlying implementation contract, and that implementation contract can be swapped in and out when issues are found. However, just be aware that there are some centralization considerations that are raised if you do this, obviously. And some people implement a kill switch, which will halt a contract from executing in the event of issues being found. However, once again, just be aware of who can execute this. Are you still running a decentralized protocol if it's just one person? And finally, get external audits. So audits are great for finding issues in your smart contracts. They're like a security-focused peer review. These auditing companies are really good at their jobs. This is what they do 100% of the time. However, they won't always catch everything, and they're not going to be the ones liable in the event of any issues being found. So just be mindful and think of them as one of many ways to implement a solid defense in-depth security strategy for building your smart contracts. So just want to summarize that smart contracts are unique compared to traditional programs. You've got open code, open transactions, immutability. So because of these things, security is obviously a very important thing that we need to take into account. But if we have an awareness of currently known vulnerabilities and we kind of learn from the mistakes and vulnerabilities of the past, and if we keep an open mind, because we don't know what vulnerabilities are going to be found tomorrow, right? There's going to be new ones that we don't know about today. So if we keep an open mind, knowing that there are going to be new ones found tomorrow, but if we try and follow the best practices, trying to keep an open mind and keeping up with the latest security-focused conversations in the community, we can kind of reduce the risk of vulnerabilities or exploits happening in our smart contracts, which will help to avoid the situation where funds are lost and things like that. So by having secure smart contracts and doing all we can to avoid exploits and vulnerabilities, it will kind of help to mature our industry and help to accelerate the adoption of smart contracts as a superior form of digital agreements. That's everything I had, so thank you for listening, and I hope everyone enjoys the rest of their SmartCon.
Awesome. Thank you so much, Harry. I love hearing these stories but a lot of them really send a jolt of terror down my spine when I hear about them, because I think, what are all the things that are going to happen to me? What are all the things I'm not thinking about? And so it's really nice to have a list I can look at to at least start making my smart contracts a little bit more secure. That was awesome.
Yeah, definitely. Right. Thank you.